Hello everyone, I'm Henry. I'll talk about improved profit inequalities for combinatorial welfare maximization with approximately subadditive agents. So what are profit inequalities? There are n boxes, let's say 3, that arrive in some arbitrary order. Each box I contains a random and independent reward xi whose distribution is di. The algorithm knows di but not xi beforehand. Upon the arrival of each box I, let's say 2, the algorithm observes the reward xi and decides whether to take xi. If the algorithm takes xi, it cannot take any other boxes, and the final reward is xi. And if the algorithm doesn't take xi, then xi expires and the next box, let's say 1, arrives, and the procedure continues. The goal was to maximize the expected reward over the randomness in the rewards and the algorithm. And the benchmark is the performance of a profit who sees through boxes and always picks the maximum reward. Turns out there's a two competitive policy for profit inequality problem. You take the reward xi, then never reward xi as greater than or equal to half of the expected maximum reward. And on the other hand, we also know that there's no policy that is 2 minus epsilon competitive for any positive epsilon. So 2 is the best that we can do. For our purposes, it's more convenient to work with an alternative interpretation of profit inequalities, which is auctions. Here, a seller has one item for sale, and n customers arrive in some arbitrary order. Each customer I has a random and independent value xi for the item whose distribution is di. The seller knows the distribution is di, but not xi beforehand. Upon the arrival of each customer I, the seller observes xi and decides whether to give the item to customer I. If the seller gives the item to I, then he cannot give the item to any other customer. And if the seller doesn't give the item to I, then I leaves and the next customer arrives and the procedure continues. The goal here is to maximize the expected social welfare, which is defined to be the total utility of the customers. And here, since we have only one item, that is just the value of the customer who receives the item. And the benchmark is again the performance of an omniscient profit who always gives the item to the customer with the highest value. And the two competitive policy translates to a pricing scheme. So you post a price P, which is equal to half of the expected maximum reward for the item, and you let the customers choose whether to buy the item. So how does that work? For example, we have only one item and we post price P. Customer 2 arrives, he asks himself this question, right? Is my value x2 greater than or equal to P, the price? The answer is no, so the customer leaves. And the next customer, customer 1 arrives, he asks the same question, is my value x1 greater than or equal to P? And the answer is yes, so customer 1 buys the item. The item goes to customer 1, and we know that the social welfare is equal to the value x1, which is at least the price P, which is equal to half of the expected maximum reward. But of course, it could be the case that the item remains unsold till the end of this procedure, in which case the social welfare is 0. So a complete analysis of the competitive ratio also considers the buyer's surplus, which is the value minus the price. In this talk, we consider a generalization of the profit inequality problem, which is the combinatorial welfare maximization setting. So here, instead of one item, we have m heterogeneous items. And each customer I has a valuation function vi, which maps each combination of items to the value of this combination. And vi is combinatorial in the sense that vi of s plus vi of t is not necessarily equal to vi of s unit t, even if s and t are disjoint. So one example is the value of a Coke is 1 and the value of a Pepsi is 1, but the value of a Coke and the Pepsi might be smaller than 2 because you can only drink so much at a time. You cannot drink both the Coke and the Pepsi at a time. The profit inequality problem for combinatorial welfare maximization is the following. We have m heterogeneous items, n customers arriving online. Each customer I has a valuation function vi, whose distribution is di. Upon the arrival of customer I, the algorithm observes the valuation function vi and irrevocably allocates some set of items si to customer I. The constraint here is that each item can only be allocated once. So for any 2 different customers, the sets of items they receive are disjoint. And the objective is again to maximize the expected social welfare, which is the sum of the value of the sets that the customers receive. And the benchmark is the performance of a profit who sees the valuation function beforehand and always makes the optimal allocation. Here's one example of how a policy works. Before customers arrive, we have 5 items and we know the distributions of the valuation functions di. Now customer 2 arrives, announces his valuation function v2, and somehow we decide to allocate the green and the yellow items to customer 2. Customer 2 leaves with the 2 items and customer 1 arrives. We decide to allocate the red item to customer 1. Customer 1 leaves with the right item. Customer 3 arrives and announces his valuation function v3. And now we give the blue and the black items to customer 3. Customer 3 leaves, and the final social welfare we get is v1 of the red item plus v2 of the green and the yellow items plus v3 of the blue and the black items. Quite something has been known for profit inequalities for combinatorial welfare maximization. The most simple case, the single item case, we know that there's a 2 competitive policy, which is threshold or price based for this single item setting. For additive valuations, which is essentially the same as the single item setting, we can just run the single item policy for each item respectively, which means we post a price for each item and let customers purchase any combination they like. And we know that if we do this, the competitive ratio is going to be 2. More general are submodular or XOS valuations. So these are truly combinatorial valuations. We know that these valuations are supported by additive ones, which means they are point-wise maximum of additive valuations. So there we have a 2 competitive policy by reducing to the additive case. And the most general setting we consider is subadditive valuations. So there we know that those valuations are approximately supported by additive ones up to a factor of O log m. So by the same reduction, we get an O log m competitive policy, and the reduction is due to the additive case. One important thing about these policies is that all these results are price-based, and in some sense, they are all reductions to the single item case. In this talk, we are going to focus on the case of subadditive valuations. A valuation V is subadditive if V of S plus V of T is greater than or equal to V of S union T. So for such valuations, we know an upper bound of O log m by reducing to the additive case, and we know a lower bound of 2, which is the same as the single item case. So that leaves a huge gap in between, right? And the common belief is that the right competitive ratio is either 2 or O log m. And here come our results. We show that there is a O log m over log m competitive policy for subadditive valuations, and we achieve this using a fundamentally different approach. So that means log m cannot be the right competitive ratio. And also we show that the same policy with different parameters also recovers the constant ratio for XOS valuations and generalizes to approximately subadditive valuations, which are more general than subadditive valuations. And before we dive into technical details, I want to discuss some further progress. Very recently, Dutin, Kesselheim, and Lucier give a price-based O log m competitor policy for subadditive valuations. And this further improves over our results, which is O log m over log m. And besides the improved competitive ratio, two important things about this result are that first, it's not a reduction to the single item case. And second, it also outlines a possible way to achieve constant competitive ratio for subadditive valuations. So this result, together with our result, is strong evidence that the right competitive ratio for subadditive valuations is likely constant or even true. Well, so far we have seen the background of the problem and our results. Next, I want to state the policy and give a quick proof sketch. So our policy and analysis are based on the welfare maximizing LP, which is the following. So the variables are XIS. XIS is the probability that customer I receives set of items S. The objective is to maximize the expected social welfare. Here, as you can see, the inner summation or the inner sum is the expected utility of customer I. And if we further sum that up over I, we get the expected social welfare. The constraints are twofold. The first set of constraints says that each item J is allocated at most once in expectation. So here again, the inner sum is the probability that item J goes to customer I. And if we sum that over customers I, we get the expected number of times that item J is allocated, which has to be upper bounded by 1. And the second set of constraints says each customer I receives one set of items in expectation. And it's pretty straightforward. So two facts are important for the welfare maximizing LP. First, we know that it can be solved in polynomial time. And second, there is a offline two-stage rounding procedure which preserves a significant fraction of the welfare of the LP and produces an integral solution. So it works in the following way. For each customer I, we view the XIS for all sets S as a distribution over sets of items because they sum up to 1. We draw a demand set SI from this distribution for each customer I. So we have n demand sets. One thing to note here is that each item J may appear in multiple demand sets. And the second step is to break ties. So to be specific, for each item J, we allocate J to a uniformly random customer who demands J. And after this step, each item J goes to precisely 1 or at most 1 customer, and we get an integral solution that is feasible. And we know that this procedure preserves a omega log m over log m fraction of the welfare in expectation. So given these two facts, our goal ideally is to solve and run this welfare maximizing LP online. However, there are some challenges. First, the valuations are gradually reviewed in our setting, which means we cannot solve the LP beforehand because we don't know the input. And the second challenge is that the allocations are irrevocable, which means we cannot break ties uniformly at random for items demanded by multiple customers because we don't always know the number of customers who demand the item. So what do? Here's our policy. Before customers arrive, we draw an integer r from the set of integers between 1 and 100 times log m over log m, uniformly at random. And for each item j, we set up a counter cj, which is initially 0. And then customers arrive. When customer I arrives, we see the actual valuation vi of customer I. And for all other customers, we draw dummy valuations ui prime from their distributions di prime. And then given the actual valuation of customer I and the dummy valuations of all other customers, we solve the welfare maximizing LP with this vector of valuations. And we extract the distribution of the demand set for agent I from the solution of this LP, which is XIS for all sets S, the solution of the LP projected to agent I or customer I. And we draw a demand set SI from this distribution for customer I. After we have the demand set, for all items j in this demand set, we increase the counter of j by 1. And after increasing the counters, we allocate any item j to customer I if the counter of j is precisely r, and j is in the demand set, of course. Well, here's an example execution of our policy. Before customers arrive, we have 5 items with counter 0, and let's say the random integer r is 2. Now customer 2 arrives, and we see the valuation v2. What the algorithm does is the algorithm draws dummy valuation u1 from distribution d1 and u3 from distribution d3. They are for customers 1 and 3. And the algorithm solves the welfare maximizing LP with valuations u1, v2, and u3. That is the actual valuation of customer 2, which we see, and the dummy valuations of customers 1 and 3. And we project the solution of the LP to customer 2, and we draw the demand set as 2 based on the solution of the LP. For example, S2 is 1, 3, and 4. We increase the counters for all items in S2. So now the counters are 1, 0, 1, 1, 0. And no item is allocated to customer 2 because no item has counter 2. Now customer 2 leaves, customer 1 arrives. We see the actual valuation V1 of customer 1, and we draw dummy valuations U2 and U3 for customers 2 and 3. And again, we solve the welfare maximization LP with the actual valuation for customer 1 and dummy valuation for customers 2 and 3. And we draw the demand set as 1 for customer 1 based on the solution of the LP. Here, let's say S1, S2, 3, and 5. So we increase the counters of those items. Now we see that the counter of item 3 is precisely 2 after we increase it. So item 3 goes to customer 1. And customer 1 leaves, customer 3 arrives. We see the actual valuation V3. We draw the dummy valuations. We solve the welfare maximizing LP with the dummy valuations for customers 1 and 2 and the actual valuation of customer 3. We draw the demand set S3 based on the solution of the LP. Now let's say S3 is 1, 3, and 4. So we increase the counters for those items. Now items 1 and 4 have counter exactly 2. So those items go to customer 3. And you may see that item 3 now has a counter of 3, but that doesn't matter. The counter of item 3 is never going to be equal to 2 anymore. So customer 3 leaves and the procedure terminates. Items 2 and 5 remain unallocated because their counters are still 1. So the important observation from this procedure is that each item can only be allocated once because the counter of the item can reach R at most once. Now let's analyze the welfare guarantee of this policy. Here the important observation is that if we were able to allocate the entire demand set Si to customer I, then the expected welfare would be the value of the welfare maximizing LP precisely. And this value is at least the value of the profit, the expected welfare from the optimal allocation. So given this observation, what we need to do is for each customer I, conditioned on VI, the valuation, and SI, the demand set, we only need to approximate VI of SI, the value of the demand set. And here the problem is in tie breaking, because if each item only appears in one demand set, we can just allocate the demand set to the agent demanding the set, and we get the optimal welfare. But that's not possible. So we want the number of customers demanding the same item to be small. And if that's the case, we can further break ties efficiently. And why is that true? Here, the key observation is that each item J is demanded at most once in expectation, which simply comes from the LP feasibility condition. So given this fact, we can translate this condition by applying a tail bound for sum of independent Bernoulli variables, which gives us that with high probability, J is demanded at most 100 times log M over log M times. And then if we further apply a union bound over items, we get that with high probability, no item is demanded more than 100 times log M over log M times, which is what we want. So now we can analyze the welfare guarantee. We fix I, a customer, and condition on the valuation VI and demand set SI. We look at the snapshot of SI after increasing the counters, but before allocating the items. And we know that with high probability, all items have a counter between 1 and 100 times log M over log M. So now we can partition these items according to their counter. So some items have counter 1, some have counter 2, and so on. And maybe some items have counter 100 times log M over log M. And we let TK be the set of items in SI whose counter is precisely K. And we know that with high probability, TK for K between 1 and 100 times log M over log M form a partition of SI. And on the other hand, we also know that customer I receives TR, where R is uniformly at random from the set of integers between 1 and 100 times 100 log M over log M. So the expected value of the set going to customer I is the expectation of VI of TR over R. And this can be written as log M over 100 times log M times the sum of VI of TK over K between 1 and 100 times log M over log M. And because the union of these TKs is precisely SI and VI is subadditive, this sum can be is at least VI of SI. And that gives our desired competitive ratio of log M over log M. Well, so the big problem remains open. We know that the lower bound is 2, and the upper bound has been improved from log M to log M over log M to log M, but the right ratio is still unknown. So the major open problem is to figure out the right compatible ratio for subadditive valuations, which is, as I believe, with high probability too. Thanks for your attention. I'll take questions whenever I can.